Welcome back, everybody. Today we're going to start in on uh, chapter 12 about solid body rotation. So up to this point, we've been dealing with and talking about the translational motion. So the motion of objects moving through space, but treating them primarily as points, as single dots. Um, and in the momentum chapter, when we talked about center of mass, we justified this a little bit because we said, well, there are forces that are interior to this pen, which are holding the pen together and making sure it keeps a rigid shape. But by Newton's third law, those forces are interior to the pen and they don't affect the center of mass motion of this pen. And so we could treat the translational motion of this large, complicated looking object as just the translational motion of its center of mass. But one thing that we haven't looked at yet is what happens when you want to let this object turn, like so. We haven't developed the physics to describe that, and that's what we're going to talk about today. So solid body or rigid body rotation means you've got a solid object, like say a pen, and you're allowing it to change its orientation, right, which is a different kind of motion than just changing the position of its center of mass. So we've been discussing over here translational motion, right? That's the motion of the pen through space, up, down, left, right, forwards, and backwards, right? But we could also have the pen do something like this, rotate around some position, right? It could be the middle. We could have the pen rotating around its end. But those are both versions of rotational motion. And in the general case, with a solid object, we could have a more complicated motion, which is a mixture of both translational motion and rotational motion. Right. So what we're going to develop here, starting now, is the physics of how we're going to deal with the rotation aspects, and then we can basically treat combination motion here as a mixture of the motion of the center of mass of our solid object plus rotation of that object around its center of mass. So there are two ways that we could have an object rotating. So it could be rotating around a fixed point. So for instance, here I'm holding the pen by the end, and as I rotate the pen, the end stays fixed. So the fixed point here around which our pen is rotating is the place where I'm holding it, right? Similarly, we could have, for instance, if I grab this paper clip here, there is a rotational motion of this arm around a hinge, right? So this would be fixed motion around a hinge, but we could also have rotational motion around objects that are sort of free to move, and those are often, it's kind of hard to pick this up on the camera, especially when the camera is vertical. That kind of motion is often around the center of mass. That's the axis around which unconstrained or freely moving objects will tend to want to rotate. And the center of mass, again, we calculated already in the previous lecture how to calculate these center of masses and how to move them. Or sorry, how to use the center of mass. All right, well, if we're going to talk about rotational motion, we have to talk about how to describe rotational motion. So we need a rotational kinematics, right? So we go right back to the beginning of the semester where we defined position, velocity, and acceleration, well, we can define those as angular properties as well, define those as rotational properties. Everybody wants to give me notifications right now. All right, so here is our rotating object. If we imagine a rotating object here, a wheel in this case, rotating around some axle, which is sort of coming out of the page at us. We could describe the rotational speed, the speed at which this thing is rotating, as an angular velocity. We ran into angular velocity when we talked about circular motion. Well, circular motion is closely related to rotational motion because every object which is a part of this wheel, every piece of this wheel will be undergoing a form of rotational motion. And so we have, in place of linear velocity, we have this quantity angular velocity, usually represented by the lowercase Greek letter omega here, kind of a curly W shape. And that's defined as the rate of change of some angle. All right, so if you have, again, let's go to this point here. If this is a point on the wheel as it rotates, we could measure its angular position as so many degrees or so many radians, for instance, from the positive x-axis. So this would be something like a 45-degree angle or a position of 45 degrees. And the rate at which that angle is changing would be our angular velocity. Again, in many cases, we're going to want to use radians, and we'll see why here today. We want to use radians as our angular units, and so the typical angular units of angular velocity would be radians per second. And if this rotation is speeding up or slowing down, if the angular velocity is changing with time, we could call that the angular acceleration. Again, the rate of change of the angular velocity, and typically that would have units of radians per second squared. For all of the points on our object, for all the points on our circle, our wheel, or our pen, they will all have the same angular velocity and angular acceleration. And this is one of the reasons for using angular velocity and angular acceleration. Notice that as I rotate the pen here, the tip of the pen moves faster than, say, the clip of the pen, because the tip of the pen is traversing a larger arc than the clip of the pen is, but it's doing it in the same time period. So the linear velocity of the tip of the pen is different than the linear velocity of the clip, right? This is why the angular quantities are useful, because everywhere along the pen we have the same angular speed, and everywhere along the pen we have the same angular acceleration, even though the linear acceleration and the linear speed will depend on where on the pen you are. So we've defined an angular position, theta, an angular velocity, omega, and an angular acceleration. And these three quantities have exactly the same relationships to each other that their linear counterparts do. That velocity, angular velocity, is the rate of change of angular position, and that angular acceleration is the rate of change of angular velocity. And therefore, we can write down versions of the one-dimensional kinematic equations that are applicable in the case of rotational motion as well. If you have a constant angular acceleration, then each of those will be true in the same way that if we had a constant linear acceleration, that the linear counterparts of these equations would also be true. And so in many ways, angular kinematics looks an awful lot just like one-dimensional linear kinematics did. It's just that instead of meters, we've replaced everything with radians, that our distance unit here is radians. It's an angular displacement. But in all other respects, all of the tools we used in 1D kinematics can still be used here, including things like the graphical method for relating things together. So omega versus t plots, angular velocity versus time plots, the area under the curve of an angular velocity versus time plot here. On an omega t plot, the area under the curve here would represent displacement. The slope here would represent angular acceleration, and so on. There's an ambiguity in the direction that we have to address. And in many, many cases, and this textbook included, they adopt the convention that if you're looking sort of face on to something, that the counterclockwise rotation is a positive rotation, sense of rotation, and the clockwise rotation here would be a negative sense of rotation. So things that rotate counterclockwise would be considered positive. Things that rotate clockwise would be considered negative. Now, that only works when it's unambiguous which is the front face and which is the back face. But for instance, if we had a rotating object like this plate from the point of view of this camera, well, obviously clockwise and counterclockwise aren't really relevant to the point of view of the overhead camera. But it still would be nice to have an unambiguous way to define the direction of that rotation, or the direction of that rotational motion. And so there is another convention that also allows us to recover the vector nature of position, acceleration, and velocity, right? Remember, in kinematics, those are vector quantities. The direction matters. They have an arrow associated with them. So we might ask ourselves, where is the arrow associated with rotational motion? And the answer is there is one, but here let me illustrate a problem with defining rotational motion. If I put this yellow piece of paper on the plate and rotate it, all right, so over here, the vector that would be associated with that rotational motion, you might be tempted to say, well, it's this way for that yellow piece of paper, and it is briefly that way for the yellow piece of paper, but as I continue rotating, all right, now it's that way. So it was a vector going this way, but now it's a vector going that way. But we haven't really changed the motion, it's just rotated a little bit. And worse, if I get a second piece of paper here, so we have the yellow and the orange. Apologies for the lack here. Actually, let's use the paper clip, which is a little bit higher contrast. So we've got the black paper clip or the yellow piece of paper. Well, the yellow piece of paper, the same rotation, the yellow piece of paper is going this way while the black clip is going that way. So that kind of motion, arrows in the direction of the moving pieces of our turning object, that's not really going to work very well to define the direction of our velocity vector, our angular velocity vector. So the convention is what we call the right-hand rule, which is that if you have an object rotating like this, that it turns out that the direction that we associate as a vector quantity to this rotation is a vector perpendicular to that rotation, pointing in this case straight up at the the overhead camera. As I turn the plate in what would look to the overhead camera to be a counterclockwise or positive direction, the arrow of the vector associated with that rotation would be in the direction of my pen, straight up out of the plane of the rotating plate towards the camera. We call this the right-hand rule, and there are a couple of different ways. There are actually several versions of a right-hand rule, but in this case, the version that's easiest is to take your right hand, that's this hand, and curl the fingers of your right hand in the direction of our rotating object. So our rotating object is going counterclockwise, and so we're going to curl my fingers here counterclockwise, and then my thumb points in the direction of the angular vector. The angular velocity vector associated with counterclockwise motion would be an arrow pointing right at the observer. So then if I turn the plates like this, where clockwise and counterclockwise doesn't make any sense anymore, I can still curl my fingers in the direction of the rotation. It's a vector that's pointing, in this case, that way, to the left of the screen. All right, so there's our vector arrow for that rotation. If I rotated it backwards like this, then I would have to take my right hand, curl my fingers in this direction, and now my thumb is pointing to the right of the screen. And that would be the motion described by a wheel here turning sort of backwards. All right, so if you're riding a bicycle, for instance, and your wheels are going like this, then the angular velocity of your bicycle wheels is to your left as you ride the bicycle. This is non-intuitive because it's the first time we've met a vector arrow which does not point in the direction of motion. But it is a very commonly used kind of vector arrow, and you will see this, those of you, for instance, who go on to Physics 2 will see this kind of a right-hand rule business all over the place when we talk about magnetism. Those of you who go on to various versions of mechanical engineering will run into this right-hand rule in various places, again, often associated with things like rotation. All right. So let's do some examples here to get used to using these concepts of rotational kinematics. So this first one says we have a disk which has an initial angular velocity, so an omega naught here of 4.5 radians per second. And it experiences a constant angular acceleration of 3.5 radians per second squared. So alpha equals 3.5 radians per second squared. And both of those are positive quantities. So if we brought our disk-shaped object back, that would correspond to a counterclockwise rotation, and one that was getting faster and faster as it accelerated, because the acceleration was in the same direction as the velocity. And it does this for a time period t here of 25 seconds, and then it asks us calculate the magnitude of the angular velocity of the disk in radians per second at the time 25 seconds after we started. So the angular velocity, and we can go back to our relationships here, and these are just the standard one-dimensional kinematic relationships, right? So the final angular velocity is the initial angular velocity plus alpha times delta t. That sounds like a good one for us to use. So the angular velocity at t equals 25 seconds, that's our initial angular velocity here, plus our acceleration times our delta t. All right, and so in this case, that's our initial angular velocity was 4.5 radians per second plus 3.5 radians per second squared times a delta t of 25 seconds. And so that's let's do the second, so 3.5 times 25 plus 4.5 gives us a final velocity, or a velocity, angular velocity at time equals 25 seconds of 92 radians per second. Then it asks us to calculate the magnitude of the angular displacement in radians traveled by a point on the disk during the acceleration. So in other words, it's asking for a delta theta, right? So theta final minus theta initial. And that's going to be our omega naught, our initial angular velocity times delta t, plus 1/2 times the acceleration times delta t squared. Again, very familiar kinematic equation here. And we can plug in this case, 4.5 radians per second, 25 seconds, plus 1/2 times 3.5 radians per second squared for 25 seconds, and square that. So 25 squared times 3.5 divided by 2 plus 4.5 times 25 gives us a displacement of, well, 2 or 3 significant, let's see, what do we got? We'll say 2 significant figures here, 1200 radians as our distance. So here was our final velocity. There's our angular displacement. And again, these kinds of problems are very, very much like the one-dimensional kinematics problems that we started the semester working on. All right, well, let's try another one. This one says, a turntable rotates with a constant 2.25 radians per second squared angular acceleration. So we have an angular acceleration of 2.25 radians per second squared. After 4 seconds, it has rotated through an angle of 60 radians. So in a delta t equals 4 seconds, it has rotated through an angular displacement of 60 radians. What was the angular velocity of the wheel at the beginning of the 4-second interval? So again, we want to know we know displacement, we know acceleration, we know delta t, and we want to know initial velocity. So probably our middle equation here, I'm going to write it as delta theta equals r omega initial, or omega naught delta t, plus 1/2 alpha delta t squared. And we're looking for angular velocity. So we're going to look to solve for the angular velocity. So this is going to be a quadratic equation where we're looking to solve for omega. But we know, let's see, we know the time, we know the acceleration. So let's go ahead and just turn a whole bunch of things into numbers. So 60 radians equals 4 seconds times our initial velocity plus 1/2 times 2.25 radians per second squared for 4 seconds squared. So this term over here, 4 squared 16 times 2.25 divided by 2. This is going to be 18 radians, and this is 60 radians equals 4 seconds times omega naught. So 60 minus 18 is 42 radians equals 4 seconds times omega naught. Take that 42 divided by 4 seconds, and that gives us 10.5 radians per second is our initial velocity. So our angular velocity was 10.5 radians per second when we started, and then accelerating at 2.25 radians per second each second. We traveled through 60 radians of rotation in that 4-second interval. All right, let's try another one here. All right, it says electric fan. An electric fan is turned off and its angular velocity decreases from 500 revolutions per minute to 200 revolutions per minute in 4 seconds. So let's just, for grins, draw ourselves a diagram. 500, 400, 300, 200, 100, 0. So 100, 200, 300, 400, 500. So this is omega in this case, revolutions per minute. Versus time. So 0, 1, 2, 3, 4, 2, 3, 4. This is time in seconds. And so at 4 seconds after we turned it off, we're down at 200. And when we started, we were up at 500. And so our angular velocity as a function of time has been doing this straight line here, in which we have changed our angular velocity by minus 300 revolutions per minute in a time period of 4 seconds. And so our angular acceleration alpha is just that delta omega over delta t. So that's minus 300 revolutions per minute in 4 seconds. But we want to calculate this angular acceleration in revolutions per second squared. So we need to convert these minutes into seconds. So 1 minute is 60 seconds. And now we can say, all right, so minus 300 divide by 4 and divide by 60 is minus 1.25 revolutions per second squared. And that's our angular acceleration along that interval. How many revolutions did we go in that interval? Well, that would be the area under that curve. We could calculate it that way, or we could calculate it in terms of a kinematic equation. So for instance, we could go final velocity squared equals initial velocity squared plus 2 alpha delta theta, and solve for our delta theta here. So our displacement is omega final squared minus omega initial squared over 2 alpha. And that's omega final, that's 200 revolutions per minute squared. But we're going to need to convert that again into revolutions per second. So 1 minute is 60 seconds, and square that. And then that's the second term here, our initial velocity, that's 500 revolutions per minute squared, again, times 1 over 60 minutes per second squared. All of that over twice our angular acceleration, which was minus 1.25 revolutions per second squared. So on the top we've got 200 times 200 divided by 60 and square that gives us 11.11 revolutions squared per second squared minus 500 divided by 60, square that, 69.44 revolutions squared per second squared. And on the bottom we're going to have minus 2.5 revolutions per second squared. So 11.11 minus 69.44 divided by minus 2.5 gives us the answer of 23.3 revolutions is the area under this curve, or the distance that our rotating object rotated in those 4 seconds. Then it asks how many more seconds are required for the fan to come to rest if the angular acceleration remains constant. So we could either sort of extrapolate this line down to 0, or again use one of the kinematic equations. In this case, omega equals omega naught plus alpha t. We're looking for time, so we can solve this for time. So omega minus omega naught over alpha is our time. Our final velocity, that's 0 minus 200 revolutions per minute and 1 over 60 seconds. 1 minute is 60 seconds. So this is the final velocity, that's our initial velocity. So we're starting here, we're calling that the first velocity, and this is the second velocity. Divide that by our acceleration, minus 1.25 revolutions per second squared. So minus 200 divided by 60 divided by minus 1.25 gives us a time interval of 2.67 seconds. Okay, so hopefully these are starting to look very, very familiar in terms of how we solve them. Again, solving these rotational kinematics problems, the units are different, but otherwise they're not particularly any different than solving the linear kinematic equations in one dimension. All right, so this is just the first part. Often what we want to do is combine rotational motion with linear motion, and there are various ways that those two things want to combine. And basically it involves thinking about our rotating object and connecting it back to the motion of pieces of that rotating object in much the same way that we did when we were dealing with circular motion, right? So when we were dealing with circular motion, we had, for instance, that the arc length around the outside of a circle was related to the radius of that circle times the angle or the angular displacement that that thing underwent. So if we have our object which started over here, or our piece of object which started over here on the positive x-axis and then rotated through some angle theta here, our point P, then it has moved through some linear distance s, which is equal to r theta. In this case, theta has to be measured in radians for this equation to work. If it did that at a constant speed, then the speed at which our point P is moving around in a circle is just that s divided by our delta t, and we can see here that that leads us to v equals r omega. We've seen that equation before when we talked about circular motion, and we're going to continue to use that equation quite significantly here. So if you're at some point P distant from whatever axis your object is rotating around here, which is at a distance r, and your angular velocity or your angular rotation of this solid object is omega, then the linear speed at this point P, a distance r away from the axis, is r times omega. If we then want to talk about the acceleration of our point P, well, now things get a little bit more complicated, because there are two ways that our object could be accelerating. Well, first of all, there's the way we've already met, which is even if the angular velocity isn't changing, the direction of our velocity vector is changing due to centripetal acceleration, because our object P is always at a fixed distance from our rotational axis, and therefore as we go around in the circle, our object P is always being accelerated radially, centripetally, towards the center of the rotation. And that has a magnitude, the centripetal acceleration has a magnitude v squared over r, which we could also write as omega squared r. So even if omega is a constant, even if the angular velocity is constant, there is a centripetal acceleration towards the center of our rotation, towards the axis of rotation. There is also, if the angular velocity is changing, then there is a tangential acceleration. There's an acceleration around the circle. That would be the rate of change of this velocity v, and that angular acceleration has a magnitude here, d omega dtr, which is, it's not written down here for some reason, but that tangential acceleration, which is d omega dt times r, well, d omega dt, that's the angular acceleration times r. And so there's a pattern here that the linear quantities of displacement, velocity, and tangential acceleration, so the acceleration around the edge of the circle, are related to their angular quantities, angular displacement, angular velocity, angular acceleration, by the same pattern, r d theta, r omega, r alpha. So you take the angular quantity in radians, multiply it by the distance to your axis r, and that gives you the tangential quantity. And then the centripetal acceleration sort of sits down here, a little bit different. Centripetal acceleration doesn't require any angular acceleration, it just requires non-zero angular velocity. So these are linear quantities: linear distance, linear velocity, linear tangential acceleration, and linear centripetal acceleration. These two, the tangential and the linear, by the way, are perpendicular to one another. So the linear centripetal acceleration is towards the center of our rotational axis, and the tangential rotation is perpendicular to the line connecting the rotational axis to our point P. So the tangential acceleration and the radial acceleration are perpendicular components, and you get a total acceleration, which is the vector sum of those two perpendicular components. These can be compared to the angular quantities of position, displacement, angular velocity, and angular acceleration. These quantities will be the same essentially everywhere on our rotating solid object. Everywhere will have the same angular velocity. Every piece of the pen here has the same angular acceleration. Every piece of the pen here has the same angular velocity. Every piece of the pen goes through the same angular displacement. But the linear velocity and linear accelerations of the pieces of the pen depend on how far from the rotation axis you are at that given moment. But these are the fundamental relationships that allow us to connect the linear motion associated with rotation to the angular quantities that we usually calculate rotational kinematics. So let's try an example and see if we can make this a little bit clearer here. So problem says a helicopter blade spins at exactly 120 revolutions per minute. So that is an angular velocity, 120 revolutions per minute. Its tip is 7.5 meters from the center of rotation. So here's the center of the blade, or of the rotating axis, and here's the blade and the tip out here, 7.5 meters from the rotational axis. It wants to know what's the average speed of the blade tip in the helicopter's frame of reference in meters per second. So in other words, we want to know how fast is this speed out here when our angular velocity is 120 RPM. So 120 revolutions per minute. Well, the relationship here is that we have a radius of 7.5 meters. We have a rotational velocity of 120 revolutions per minute. And the connection there is that the velocity, the linear velocity, is r times the angular velocity. So that's 7.5 meters times our angular velocity of 120 revolutions per minute. But we want our speed in meters per second. So we got to convert our revolutions to radians, and there's 2 pi radians per revolution, and 1 minute is 60 seconds. So we take 7.5 multiply by 120 multiply by 2 pi and divide by 60, and this gives us a speed of 94 meters per second. And we could do another one. This one says a stone in a sling is swung in a circle of radius r equals 0.65 meters. So we have a radius of 0.65 meters. We have our rock here in a sling. So 0.65 meters is the distance from the center where we're holding the rope to where the rock is. And the angular velocity here again, in this case, 12.5 radians per second. So it wants us to calculate the linear velocity in meters per second. That's this speed out here. And the centripetal acceleration, a sub c, in meters per second squared. All right, so linear velocity, again, is r omega. So that's 0.65 meters times 12.5 radians per second. So 0.65 times 12.5 gives us 8.13 meters per second. And our centripetal acceleration is r omega squared. So that's 0.65 meters times 12.5 radians per second squared. So 12.5 squared times 0.65 gives us a centripetal acceleration of 102 meters per second squared. All right, there's one place where this connection, one kind of problem where this connection between linear motion and rotational motion is particularly common, and this is the idea of rolling without slipping. So this happens all the time. For instance, here we could roll the plate, and if it's not slipping, then there's a relationship between how fast it rotates and how fast it moves. And the condition of slipping or not slipping means that at the point of contact, here between the road and the wheel, at the point of contact between the road and the wheel, there's no slipping. This would be slipping, but if there is no slipping, that means that the relative motion of the road and the wheel is zero, that there's no velocity between the road and the part of the wheel that is touching the road. And so to do that, we have to have a combination of two motions. There's the center of mass motion of the wheel, which is moving at some velocity v, some linear velocity v, and there's the rotational motion around the center of the wheel, which is symmetric around the center of the wheel, but there's a change in perspective going from the motion centered around the axle of the wheel to the motion relative to the road. So the center of the wheel is moving at some velocity v relative to the road. But in the wheels, in the sort of axle-centered point of view, all that's happening is that the wheel is rotating around the axle, and indeed the road would be seen from the wheel's point of view as going backwards at that same velocity that the road would see the wheel moving forward. And here is where we get the constraint, right? If the road and the wheel have to not be moving relative to each other at the point of contact, then that means, well, again, from the center of mass, from the wheel's point of view, the bottom part of the wheel here is moving backwards at some speed v equals r omega. And if it's moving at the same speed of the road, then the road must also be moving at that same velocity. From the road's point of view, the road isn't moving, the wheel is moving at this velocity v. So when you have an object which rolls without slipping, its center of mass velocity must equal r omega, the linear velocity around the edge of the wheel. So this velocity equals r omega is also the rolling without slipping condition. So anytime we have an object that moves without sliding, that rolls without sliding, then there's going to be some relationship here between the center of mass motion, linear motion, and the rotational velocity of our rolling object. Now let's go back here to the center of mass frame. The top of the wheel is moving forward relative to the center of the wheel at the same speed that the bottom of the wheel was moving backwards. Well, from the road's point of view, that means that the bottom of the wheel wasn't moving at all, but must mean therefore that the top of the wheel is moving twice as fast. And the actual motion from the road's point of view of a piece of the wheel is this sort of a looping, arcing motion, which is fastest at the top of the wheel and briefly stops entirely at the bottom of the wheel. And for instance, if you look at this photograph of a bicycle, this is not a doctored photograph, nor is it out of focus. What you can see is that at the bottom of the wheel, where the rotation relative to whoever was taking the picture should, or the motion relative to the ground, which is relative to whoever took this picture, is the slowest, you can see that the spokes of the tire are very much in focus. But at the top of the wheel, which was moving relative to the ground, the top of the wheel, the spokes are all blurred out, and indeed so you can see some motion blur even in the center of the wheel. It's only the bottom of the wheel that is sharply focused here because that wasn't moving relative to the camera. So let's apply this rolling without slipping condition. This is a pretty simple version of it, but we'll get plenty of practice using the rolling without slipping condition. So it says our soccer ball, here's our soccer ball, has a radius of 22 centimeters, and it's rolling without slipping along the ground at a speed, a linear speed here of 2 meters per second. What's the angular velocity? In other words, how fast is our ball rolling as it rolls? Is our ball turning as it rolls? Well, the rolling without slipping condition is that the linear velocity is equal to r times the angular velocity. In this case, we've been given not radius but diameter, so that's diameter over 2 times our angular velocity. And we're looking for angular velocity. So take our angular velocity here. That'll be twice our linear speed divided by the diameter of our ball. So that's 2 times 2 meters per second divided by 0.22 meters. So 2 times 2 divided by 0.22, lots of 2's in this problem, gives us an angular velocity of 18 radians per second. Right? So not hard to use, just got to remember to use it, this rolling without slipping condition. And like I said, anytime you've got a turning object that's connected to a not turning object, we'll use this rolling without slipping condition quite a lot. Indeed, to finish off, we're going to look at a slightly more complicated version of rolling without slipping, or maybe we should call it turning without slipping, looking at the various pieces of a bicycle transmission and its drive chain and the speed of the bicycle. So it says here, a bicyclist notices that the pedal sprocket, that's this front sprocket here, has a radius of 11 centimeters. So the radius of our pedal wheel here is 0.11 meters. While the wheel sprocket has a radius of 5.5 centimeters. So that's the small gear at the axle of the rear wheel there. So we're going to call that, he calls that the wheel sprocket. So the radius of the wheel sprocket, R sub W here, is 5.5 centimeters or 0.055 meters. The two sprockets are connected by a chain which rotates without slipping. So the gears of the sprockets mesh with the chain and doesn't allow the chain to slide against those wheels. So the rotational velocity around the pedal must match the linear velocity of the chain. And it has to do that at the front sprocket and the back sprocket. And therefore, the linear velocity around this wheel must match the linear velocity around that wheel. And that's a constraint that you'll see not only in chain drives like this, but pretty much all gear systems in general will have that condition that the linear velocities at the edges of the gears, or in this case, sprockets, must match. The bicycle wheel has a radius, that's the wheel itself, has a radius R, capital R here, which is 63 centimeters, so 0.63 meters. When pedaling, the bicyclist notes that the pedal rotates at 1 revolution for every t equals 1.6 seconds. So the angular velocity of the pedal is 1 revolution per 1.6 seconds. And so the question becomes then, what is the angular speed of the pedal sprocket in radians per second? So first we have to convert this into radians per second. Well, 1 revolution is 2 pi radians. And so that's going to be 0.6, or 1 revolution divided by 1.6 seconds times 2 pi gives us a speed here of 3.93 radians per second. So that's the first question answered. Then it has us calculate the linear speed of the outer edge of the pedal sprocket. So calculate how fast the chain is going to move around the outer portion of the pedal sprocket. So the radius, or the speed there of the pedal sprocket, that's going to be the radius of the pedal sprocket times the angular velocity of our pedal sprocket. And again, to use these equations, we need to be in radians per second here for the angular velocity. So that is our 0.11 meters times 3.93 radians per second. So that gives us a linear velocity of 0.432 meters per second. Okay. Then it says calculate the angular speed of the wheel sprocket back here in radians per second. So this smaller little sprocket at the back has to have the same linear velocity around the outside, that the linear velocity of the wheel sprocket must equal the linear velocity of the pedal sprocket, which was also going to be the radius of the wheel sprocket times the angular velocity of the wheel sprocket. And if we're looking for angular velocity, then that's going to be our linear velocity divided by our radius. So that's our 0.432 meters per second, because again, the chain moves at 1 speed everywhere around the chain, that 0.432 meters per second. Divide that by our 0.055 meters for the wheel sprocket, and that gives us a speed of 7.85 radians per second. That's the angular velocity of the back wheel. Then it asks us to calculate, well, what's the linear speed of the bicycle in meters per second, assuming the wheel does not slip across the ground. So now the bicycle has a radius r and an angular velocity. Well, the angular velocity of the sprocket wheel has to also be the angular velocity of the wheel itself. So that's going to be our 0.63 meters times our angular velocity of 7.85 radians per second. And that gives us a linear speed here of 4.95 meters per second. So the bicycle is moving at 4.95 meters per second. And we could calculate that knowing just how fast the pedals were moving and the relative size of the pedal wheel up here and the drive sprocket back here and the wheel itself. Then the problem asks, if the cyclist wanted to travel at a linear speed of 3.5 meters per second, how much time in seconds should elapse as the pedal makes one complete revolution? In other words, let's work backwards from a different velocity. So if our velocity here is 3.5 meters per second, well, that velocity is going to be the wheel's radius times, again, the angular velocity of our sprocket, which tells us if we then solve for the angular velocity of our sprocket, that's going to be our linear velocity divided by the radius. So that's 3.5 meters per second, the speed we want to move at, divided by the radius of our wheel, 0.63 meters, gives us 3.5 divided by 0.63. An angular velocity of 5.56 radians per second. That's how fast the wheel there would have to rotate. The chain then must have a linear velocity, which is the radius of the sprocket wheel, or the wheel sprocket, times the wheel sprocket's angular velocity. So that's the 0.055 meters times our 5.56 radians per second, or 0.306 meters per second. That's how fast the chain would be moving. Then we can convert that into how rapid must the pedal wheel be rotating, because that must also be the pedal wheel's velocity, linear velocity, which is the radius of the pedal sprocket times the angular velocity of the pedal sprocket, and we're solving here for angular velocity. So that's going to be our linear velocity divided by our radius, so that's our 0.306 meters per second. That's the speed of the chain, and our 0.11 meters gives us a 0.306 divided by 0.11, an angular velocity of 2.78 radians per second. And then if we want to convert that into how long should it take to pedal around, well, our angular speed of the pedal wheel is 2 pi radians divided by the time it takes to go around, and so the time is 2 pi radians divided by our 2.78 radians per second. So that comes out to be 2.26 seconds. So every 2¼ seconds, the pedal has to turn all the way around if you want to move at 3.5 meters per second. So this was a whole bunch of applying that same V equals R omega rolling without slipping condition or turning without slipping condition, applying it over and over again between all the different aspects of the bicycle transmission, from the pedal wheel to the chain, from the chain to the wheel sprocket, from the wheel to the ground, and back again. All right. Having now laid out the kinematics, the descriptive motion for rotation, next time we will tackle Newton's laws in rotation world and talk about torque. Till next time.